Mark, all yours.
So thank you, Robert. So the introduction to this talk is actually the conclusion of my talk 2 years ago. And what I want to cover in this, in the next 25 minutes is the fact that at ILL we're delivering science and innovation and developing capability for European neutron scattering, that we are building on our strengths, and that is our highest intensity continuous neutron beams, and they allow us to study the smallest samples, do time-resolved measurements, and polarized neutron experiments. And we are, of course, preparing for the future that goes beyond 2030, and neutron sources, as we've just seen, will be closing down or just have closed down. ESS is certainly ramping up. And we will be taking great care of our unique neutron source, delivering the endurance upgrade program. And of course, we need funding, so these agreements with the associates and the scientific members will be renewed. So just as examples of the small samples, there's the ones we use for levitation and, for example, a protein crystal, and these typically weigh fractions of a milligram. So that's what you can do with very intense neutron beams. The ILL is a user facility, so we were absolutely delighted this summer to welcome Slovenia. Slovenia is now our newest scientific member. So I'd like to spend a few slides on the current situation, a snapshot, if you like, of the current situation, and that definitely includes COVID. And when we got back to work in May, we had a couple of major projects that we wanted to complete before starting the reactor in August. And one of those was the installation of the H4 beam tube, which serves D3, a single crystal polarized neutron diffractometer. And in these photographs, you see the technician, Sebastian Viel, reassembling the instrument after the beam tube installation. So that instrument will be back, but it will also have new capability, a wide angle detector and polarizer for liquid diffraction. And that complements our existing capacity in this area, which is provided by D4. And this is the sort of work that's been done there, looking at, for example, structures around calcium in solution. So this is a combination of experimental and simulation work, and the idea actually is through this work to improve force field parameters for calcium and other atoms in these solutions. And when you want to extract detailed information, structural information, then one way to do it is to take the differences of scattering curves, and that's what you see in the data on the right, both from the experimental data and the simulations. And if you read the paper, you'll actually see they've taken differences of difference curves. And you can only do that if you've got an extremely stable source like we have here. The second major project was delivering DALI, the second protein crystallography station. This photograph just shows the neutron velocity selector. LADI, the first protein crystallography station, uses a filter. And what we've learned in this project is that the velocity selectors actually going to be better than that and will give higher transmission, so more neutrons at the sample. So DALI will be an improvement over LADI and will subsequently make the same improvement to LADI. This is the guide that takes the neutrons from that velocity selector through to the instrument. And this is what it looks like today. It's got a temporary air-conditioned tent around the instrument itself so that these delicate protein crystals can actually be used for commissioning. And this is the typical sort of data we get from, we're getting already from DALI, but the data on the left here is the first data set measured on LADI this cycle. And the sort of thing they do, as you may well know, is look at these very complex protein structures, which are essentially determined by X-rays at the synchrotron next door, for example. But what's missing, of course, in the X-ray determined structures is the information about hydrogen. So in the inset there, you see hydrogen bond networks, structural water, and these are essential in understanding the way the active site works in these proteins, and indeed the way drugs would bind in the active sites if you wanted to stop that action. And this example here concerns pKa, so it's an enzyme, and understanding it is essential for treating fatal diseases like cancer, diabetes, and cystic fibrosis. So if you want to look at this, it's been published and the references are below. So we then started the cycle on the 11th of August, and it will finish on Tuesday morning next week. Everybody at ILL was ready and raring to go. You can't see that they were all smiling in these photographs, but these scientists and technicians, I think they all had a twinkle in their eye and were delighted to be back on the experiments. Some of the users were able to come, about 25% of our normal number of users. This was just enough to allow us to make full use of all the beam time. And most of the experiments we selected were simpler experiments so that we could run them without user presence. But as you see on the right, actually, it's something that Bastian Merkisch alluded to this morning. It's a cold neutron electric dipole moment measurement by Florian Pixar and his team. So that was a major effort on their part to install this very sophisticated equipment on PF1B. Just to show you a nice photo, as Bastian said this morning, these measurements are normally done with ultra cold neutrons and not cold neutrons. And this is one of the big projects that we're completing now in endurance, and I'll come back to this in a minute. It's SuperSun, so it's an ultra cold neutron source. It's a cryogenic source, and these are expected to make a real step change in ultra cold neutron provision and the science that can be done with that. And the conversion volume is this horizontal cylinder, so it's about 4 meters long, and it's cooled to 500 millikelvin. And it's in this volume that the slow neutrons are essentially cooled to about walking pace. And this is Skylar Deckenkolb, who's the instrument scientist on the SuperSun project. And this should be delivered towards the end of this year, and we'll have the first ultra cold neutrons for the cycles next year. So something that's already been mentioned by Andy Gertz, COVID has been an opportunity to try out remote access to instruments, something we were already developing for other reasons, and something that's emerged from this PANOSC activity that we heard about this morning. The implementation at ILL is called VISA, so it's cloud-based applications that allow us to allow you to run the instruments remotely, have access to the data, and treat the data remotely. So the idea in this cycle has been not for us to do the experiments for you, but for you really to do the experiments as if you were here. And the feedback that we've had about this has been very positive. Of course, it's not complete or perfect, but it really is a very good start, and we'll be certainly developing that further. So COVID was also an opportunity, or is also an opportunity for research. We have a very strong biology activity on the EPN campus here with our neighbors at the SRF, the EMBL, and the Structural Biology Institute. So some of the first people to come back to work were our scientists who are interested in biology, and there's about 20 of them at ILL. You see them here. And they started to put together ideas with their collaborators about neutron experiments that we could do, and in particular prepare the samples, deuterated samples that are essential for this kind of work. And so we're now doing some of these experiments. So there were 6 DDT proposals and about a dozen experiments, some small angle scattering, and some of the samples in this rack here are indeed COVID samples. One of the DDT requests was for a reflectometry experiment. So the idea here is to look at the fusion peptide, which you see on the lower left, and it's part of this spike protein that binds and interacts with the cell membranes, and then allows the virus molecules to enter into our cells and replicate. So the reflectivity data on the right shows how the fusion peptide interacts with the membrane. So that structural information depends crucially on having deuterated lipids as were used here. But what you also need to know is not just the structure, but to what extent, for example, the membrane is softened by this interaction and allows other molecules to go through the membrane. And that's been studied using neutron spin echo on IN15. So that's a snapshot of where we are. You've heard a little bit in those first few slides about the things we're delivering, for example, SuperSun, D3 liquids, and DALI. And what this slide does is just give you an overview of the endurance program and more that really is the basis of this new capability that we're delivering at ILL. So endurance is a 60 million euro project or program running from 2016 through to 2023. And in the upper half of the slide here, you see a range of projects, so new instruments, upgrades, infrastructure, and technology that we've either have delivered or are in the process of delivering. And I won't go into each one of these. Some of them will figure in the following slides. But there's still more to come. And in the lower half of the slide here, we see that we have in execution phase an upgrade to the next imaging station, which I'll say more about, but also the H24 guide system, thermal guide system in ILL7, and 3 new instruments. And then we have a range of other projects that are finishing their feasibility phase and are ready to move into execution. So one of them concerns the cold neutron guide H15 and 4 instruments, and that neutron guide has actually been ordered now. And then some individual projects that are, as I say, finishing feasibility and ready to move into execution. And the photographs that you see on the right, well, they're just illustrative. The one in the top right is a Langmuir trough. So this is part of the NESI program of sample environment projects. And the photograph on the lower right shows the radial oscillating collimator for extreme D, a new extreme conditions diffractometer, and that was being tested this week. So before we go on to the hardware and the science and new capability that will deliver, as Helmut mentioned, you know, there's a lot of focus, and we heard it from Andy Gutz, on data and software, and in particular, a big focus on the opportunities offered by artificial intelligence and machine learning. And we had a great workshop at the end of last year. It was organized by ILL, ESRF, and STFC. We filled the auditorium at the ESRF, more than 160 participants. And that was a great opportunity to share ideas, to make collaborations. And since then, we've been delivering some applications. So triple axis spectroscopy, small angle scattering, and diffraction. And I've got the same figure that Helmut showed this morning. And it's the way machine learning can be used to probe an excitation spectrum. You may not know anything about this, and then machine learning will quickly determine the most effective and efficient way to measure this excitation spectrum. And of course, if you've got prior knowledge, well, you should build that in as well. But there are really significant savings in beam time to be made with this type of approach. And this really came out of a collaboration from the workshop with Lawrence Berkeley National Lab and the group of Jamie Sethian. So some of the new capability we're delivering actually involves X-rays. We've got an excellent X-ray source next door, but we can have some in-house X-ray capability, which is extremely useful. And so the one illustrated here is a single crystal diffractometer. And as I'm sure you know, neutron diffraction data is almost always published with X-ray data. So by having this instrument in-house, we can systematically collect data on the same sample and under the same conditions. So you see in the middle, neutron powder diffraction data from D2B, and then the results of analyzing X-ray diffraction data in the lower plot. And this gives exquisite structural information on complex molecular structures like the one illustrated on the right, which is a metal organic framework. So this single crystal diffractometer is available to our users through the user club, and in particular the easy access proposal system. So we have X-ray capability in situ in some cases, and here it's on D22, a small angle scattering instrument. So this SAX instrument is shown here. It's a long tube like a neutron small angle scattering machine, and this photograph enables you to see who has been working with us to provide the instrument and the collaboration. So we're very grateful to Tobias Unruh and colleagues from Erlangen University for the collaboration and the funding from the BMBF. So if we look at this close up, when the photo comes, you see here, this is a photograph of the sample position. So the sample is here. It's not in its normal configuration perpendicular to the beam, because now we've got two beams, an X-ray beam coming from the left and a neutron beam coming from the right. So it looks very compact. It will be difficult to have, or it'll be challenging to have a sample changer in there. It'll have to come in vertically. But this is really a configuration that's going to enable new science. And some of it's been published this year, and it's a nice example on how you can watch gold nanoparticles grow using small angle scattering. So on the left, you see the X-ray data, on the right, the neutron data. And what's really striking here is that the two different data sets have completely different forms and different time evolution. So it really tells you that these data sets are complementary. They're watching the same process at the same time, and they're giving complementary information. And that's reported in this paper that was published this year in the Journal of Applied Crystallography. Another instrument where we've got in situ X-ray capability is for imaging. So the instrument was called D50. It's now become a public instrument, and it's called NEXT. The initial work was developed with the local university. They are experts in X-ray imaging, but they quickly became very proficient in neutron imaging. And the instrument already has really excellent performance. So resolution of a few microns, simple images can be taken in milliseconds, tomography in seconds. And as I say, X-ray capability is there, and actually almost all experiments use a combination of neutron and X-ray imaging. And the sort of thing they can look at is illustrated on the top right. It's the take-up of water by plant roots. And you can use HD substitution here very nicely, because you can essentially let D2O flow into H2O, so you can see how this water uptake takes place. Another very good subject for neutron diffraction is batteries, where of course lithium is a key component. And again, we've got this very nice isotopic effect and difference between lithium-6 and lithium-7 in terms of their scattering and absorption. So these Duracell type batteries have been studied by X-ray and neutron diffraction. This is quite a complex set of plots, but the upper plots come from X-ray imaging, and the lower plots from neutron imaging. And the first thing to note simply is the contrast in the two cases is completely different. And essentially, the simple message is that X-ray imaging sees the electrodes and neutron imaging sees the electrolyte, i.e. the lithium. And one very simple thing to notice here is that here in the center of the battery, you see electrolyte depletion as a result of the cycling of the battery. And of course, there's many fine details that can be extracted from this data. And this work was published not so long ago in Nature Communications. So a new instrument, no X-ray capability in this case, wide-angle spin echo. So this instrument has taken some time to deliver. It was a very, very challenging project, but now it's in user service, doing user experiments. For those of you who know spin echo, you normally see the big magnetic coils horizontally disposed in the scattering plane, and that traditionally or typically limits the solid angle of detection, and that's one of the handicaps of the spin echo technique. So what you see in this photograph is that the coils have been turned vertically, essentially, and if you think about it, the magnetic field lines that are in the scattering plane in the middle of this photograph are the same as you would get from the horizontal coils, and they allow the neutron spins to process around those field lines as they go from the sample here out to the detectors on the edge of the instrument. So this way we get a very wide scattering angle, which really increases the count rate on this type of instrument compared to its predecessor, IN11. So here we see a table of the characteristics. We can now cover, because of the angular coverage, a wide Q range. And when we go to longer wavelengths, we can get out to very long Fourier times of about 20 nanoseconds. And just to demonstrate that this really is working and delivering science, well, here's a set of relaxation data from a microemulsion sample, about 15 Q values measured in less than an hour. And just so that you can work out for yourselves how much better this instrument is than 911, this type of data would have taken days to collect previously. So really the throughput on this instrument is going to be much, much higher than on 911. Another new instrument is Panther, a thermal time of flight spectrometer. It's been a little while coming. It's hidden away now behind these walls in level C. We turned the beam on, or Bjorn turned the beam on for the first time on the 6th of February. And since then, we've been collecting first data, in some cases with users. So this is diffraction data, but we don't build a spectrometer just to measure diffraction data. We like to see SQ omega maps like this. And if you have a trained eye, you can see the Bragg peaks, but also the acoustic phonons that emerge from the Bragg peaks, some quasi-elastic scattering, and then at higher energy transfer, some indication of optic phonons. So that's progressing very well. There's some more developments to come. There's polarization analysis using these helium-3 spin filters, the so-called pastis spin filters. These are the ones from IN20. And at the end of the year, we should have the rest of the choppers delivered. So there's a system of 5 choppers to be installed. And when they're there, the upgrade will be complete, and this instrument should be 60 times better than IN4. So IN5 is another time of flight spectrometer called Neutron that has had upgrades, but more is still possible. And here we simply changed the end of the guide and added a variable M focusing nose. And this gave a factor of 3 increase in count rate at the sample at nominal wavelength, but almost a factor of 10 at shorter wavelengths down to 2 angstroms. So really increasing the operating range of the instrument. And so that will facilitate the type of measurements you see on the right here, and in particular going out to higher energy transfer in neutron energy loss. IN5, you can push it to longer wavelengths to improve the energy resolution, but then you run into the essentially the dynamic range of IN16, which is a backscattering spectrometer. And this has been increased recently through this BATS upgrade, where we use choppers on the incident beam to essentially increase the possible energy transfer. And there's a sophisticated pair of choppers which have different size openings, which allow the energy resolution and therefore the flux to be tuned. So the data shown in the bottom left shows a comparison between IN5 and BATS. So we get much better resolution from BATS using the backscattering technique, but actually a much wider Q range as well, and that's very important. And this type of instrument is often used for quasi-elastic scattering, and this is now, and here's an example that's been published. It's on drug molecule diffusion in gels, and it's by Cathy Edkins from Manchester. So this instrument, this option on the instrument's used about 30% of the time at the moment, and there's an upgrade ongoing which will allow further improvements here. So a final science example is nuclear physics. And we celebrated last year 150 years of the periodic table. And you may have thought that everything was known about the elements in the periodic table, at least up to 104, where the elements are in principle stable enough so that you can measure them. Well, it turns out that that's true with the exception of promethium, which is number 61. And there are very few long-lived isotopes of promethium. So we set about providing or producing this long-lived isotope so that it could be used for an ionization potential measurement. This was a crucial piece of information that was missing from the periodic table. So we started from neodymium-146, add a neutron to get neodymium-147, which then decays to promethium-147. And that was then extracted from a whole host of other species and then delivered for the ionization potential measurement. So that's a great thing to do for nuclear physics. You might say there's no potential in that because we've just measured this ionization potential and there's no more to do. But the other things like this we do are producing doses of lutetium-177, and we've produced about 10,000 doses for cancer therapy, and we're developing terbium-161 for the same application. So what's still to come? Endurance next year, after the 3 cycles that I'll tell you about, we'll be installing this H1H2 beam tube.
A couple of minutes, Mark.
Yeah, 2 more slides. The H1H2 beam tube, it's about 4 meters long, 2 branches which deliver cold neutrons and thermal neutrons. So here we see the H24 branch, which will be renewed, and 3 new instruments, D10, Ion 13, and Extreme D. And we will start the installation of the H15 cold neutron guide system. So we have to keep operating, of course. So this is the planned schedule that you can find on the internet for the next few years. So we plan to deliver 3 cycles at the start of next year, and then a long shutdown to allow us to install H1, H2, and these other guide systems and a range of other work as well. So, and after that, we want to get back into some equilibrium where we're delivering 3 cycles or 160 days of neutrons per year. So that's what I wanted to tell you about ILL today and tomorrow. I'd like to leave you with this slide which summarizes 50 years of achievement at ILL. But the key message is that ILL really is a vibrant scientific facility, and actually it keeps getting better. So thank you for your attention.
Thank you, Mark. So as you said, well, 50 years in half an hour, very good. So we have some questions. Klaus Dieter Lists is dominating them, so I'd like to invite some other people to ask questions. Actually, I'll start with his second question, which is about in situ X-ray and neutrons simultaneously. As he's saying, because they're coming from different directions, does it really make sense to combine them because they're very different probes? And are they really measuring the same thing at the same time?
I think there's in some cases it's a convenience. It's a convenience rather than essential needs to have to have them both at the same time. In many cases, you really do want to have the neutron and the X-ray data, because I think the SANS example was spectacular in the way it's complementary. But when you're cycling systems, and when you have, for example, soft matter systems that are quite fragile, then you really want to do these things at the same time on the same sample. So I do believe that that it really is essential to have this in situ capability for a significant fraction of the experiments that use both techniques.
Okay. I'll interpose a question from Alan Hewitt, who says it's good to see testing of the extreme D collimators, but the instrument itself is still to come, even though the proposal is now 15 years old. So when will it actually make it to the delivered list?
It'll be on the delivered list in September 2022. So unfortunately, it's been delayed. The installation of the manufacture of the H1H2 beam tube is very challenging, and that's been delayed. And we can't install the H24 guide and instruments, including Extreme D, until we install H1H2. In principle, it would have been installed already, but now the planning is September 2022 for first neutrons.
Okay. Bill Sterling's just snuck in a question, so I'll get Bill's question. Good to see many projects coming to fruition. Is the pandemic leading to major delays with endurance?
We have looked very carefully at that. There are some delays to what we call independent projects that aren't linked to other projects, so they're easier to handle. And there are no significant delays in that. Either we're delivering projects before the long shutdown that's coming up in 2021, 2022. For example, a wide-angle detector on D22 will be installed at the end of this year. Or the delays come within this long shutdown, so that we'll still be ready to start with these upgrades after the long shutdown. So no significant impact of COVID so far.
Okay, and then the final question then, again from Klaus Dieter, but it was linked to what I was going to ask myself about remote access and the pluses and minuses of that. And he's making the point that it decouples the science from the instrumentation, and therefore you lose the learning process there. And even that, of course, if you decouple the users, you may decouple funding. So what's your views on the pluses and minuses?
I think there. So first of all, a minus is it's a lot more work for us. The users do a lot of work when they're here. The plus is allows us to be more efficient in some cases. For example, scientists this cycle have been mixing up experiments and staying with one instrument configuration for longer, rather than keeping samples and changing configurations. So there's some gains to be made that way. There are other gains. I mean, it may be more, it is more difficult for people to travel at the moment, and that will continue to be the case. And so I think the way ahead is to have a wise mixture of remote access and physical presence. But I would just say one more thing. I think it is essential that people who use ILL must come to the ILL at some point, and that preferably before they do remote access experiments. So they really do see what is here, what doing an experiment here entails. And as most of our work is collaborative, that we have an opportunity to really develop those collaborations.
Yeah, okay, thank you. And I would echo that. I mean, I would say people work with people and not with machines, and that's very important. Yeah. Okay, so thanks very much, Mark. We'll now move on to, here's your round of applause. The next talk is from Marcus Strobel from PSI, who's going to talk about industrial applications. So all yours, Marcus.
Good afternoon. Thank you for the introduction. I'll try to share my screen. Good. So yes, thank you for the opportunity. I'm going to speak about industrial applications at ThinQ at PSI, and in particular, I will introduce you to the workings of my group with industry. We are doing mainly Neutron imaging and diffraction. And the Paul Scherrer Institute is a large research institute in Switzerland. It consists of several large scale facilities like the Swiss light source, but also the ThinQ, the neutron source, and we run proton therapy. We do radiopharmacy research. We also lately got in operation the free electron laser. We have hot labs, and we do energy system research. And all these parts of the organization have, of course, industrial contacts, industrial projects. But what I focus on here is, of course, the access of industry and the use of industry of beam times, of beam time instrumentation. And here there is, of course, in particular, the Swiss light source and the ThinQ, which are of importance in providing services of beam time to industry. And we are part of the Laboratory for Neutron Scattering and Imaging, which you see here, the LNS. And our group is the Applied Materials Group, formerly the Neutron Imaging and Applied Materials Group. And we are taking a large load of the industrial requests for neutron measurements, and this I will talk about. But our group is running 3 instruments, a dedicated thermal neutron imaging facility called Neutron, cold neutron imaging facility ICON, but also POLDI, which is a strain diffractometer. And we are also partially running the BOA, which is a polarized beamline for polarized neutron imaging. And of course, we are taking part in the ESS through the Swiss in-kind contribution, where we're constructing and help constructing together with the TU Munich and the ESS, the neutron imaging instrument Odin. Otherwise, our main activities, of course, lie in these 3 columns. That is method development, and then, of course, material science and science, user service, but also industry is an important column. And accordingly, we have also reserved beam time. The biggest part, of course, goes to users and science, but significant fractions are reserved for industry. This is up to 1/3 of our beam time that we reserve for industry, so that we're also able to react flexibly to requests. And for industry, time is often money, so you have to be able to react quickly. What we do furthermore is development of technology, which is important for our scientific work, and this is software for imaging. We push, of course, the resolution boundaries for imaging, or we do optical devices that we need for new methods or optics. Under this technology development, there is, of course, also the regime of developing scintillators for imaging. This is a long-standing activity in in our group, and one of the latest achievements was the introduction of gadolinium 157 enriched Gadox scintillators. They are the best scintillators for highest resolution imaging. So when you go to resolutions of a few micrometers, as we heard before, and what we do when we have developed such products, we commercialize them also, and we have a long-standing collaboration with a company in the area, with Tritec, which is one of the main providers of scintillators for Neutron imaging, but they also have a lot of other products, of course, and they help us, and together with them, we sell the scintillators that we develop, but also other like this optical resolution mask that you see here. So we collaborate with this company to commercialize our developments and make them available, and so they spread over the world. Lately, we're working a lot on fast Neutron scintillators, and such projects often get also funded, get smaller fundings for product development, and we always do this in conjunction with this company. And this company, of course, also uses us when they have customer requests, that we give advice and our expertise to that the customers get the products that they need and that they want. Then we look on how beam time service is organized at BSI, and we have industry and the BSI, and of course the BSI runs a technology transfer team section, and they are supporting all industry work with their contracts. They support spin-offs. They do contracts, NDAs, so all essential things for industry work. But the working themselves and the beam time sales for SLS, for our Swiss light source, for example, runs through a separate company which is called the SLS Techno Transfer AG. So this sales basically makes the dealings with the beam times at the Swiss light source. For the neutrons, that is different. Here, our groups of the instruments in the laboratory for neutron scattering, they deal independently with the industry. They get, of course, support by the technology transfer for doing contracts, but all the contracts, the workflows, and the money flows, they run directly between the industry and the groups. And that also means that when the group puts work into industry, then also the budget increase that comes from the industry payments goes directly into the group, and accordingly, there is also motivation to do such work. Lately, there is a new company, basically a public-private partnership, which is called Anaxam. They have been founded by the end of last year, and they are aiming on increasing the visibility and the use of neutrons and large-scale facilities at BSI and in Switzerland for industry. And so we also get customers through Anaxam and this company, which is actually run as CEO by the former coordinator for such works in my group. So he has moved and is now CEO of this company. But this company is not, of course, only working for us. It works for the whole large-scale facilities that we are running, so the LNS, but also the SLS and other facilities in our institute. So, of course, a lot of research with a lot of work with industry also runs via research projects. So this is something that I will not focus on. I think this is done everywhere a lot, but an example I want to show you, this is additive manufacturing, where we have a strategic focus area here in Switzerland, where there is funding for projects developing these processes. And here we are particularly involved in a project which aims for additive manufacturing of precious metals. This is, of course, important here in Switzerland for the jewelry and the watch industry, and correspondingly, of course, in these projects also there is industry involved, and together with industry, we develop these processes further and do investigations and characterizations. But this project is not what I focus on here in this talk. What I really focus on is works where industry comes, asks for a service, we provide the service, we do a deal, and this is it, and we do not really do research together. So this is a different topic. So when we now look at my team, at the Applied Materials Group, we see we have for each instrument about 2 staff. Partially this is a senior scientist with a postdoc, but we have extra 2 people here under industrial applications. And then of course we have project staff, postdocs, PhDs, and also some trainees and external associates. But when we focus on industry, we have 2.5 people which are paid out of our industry income, and which therefore also focus quite some of the work on the industry collaborations and have to do the main bunch of the work that comes in through industry. However, all the team is of course motivated to support this, and most of the people shown here will also have involvement in one or another industry project. But these 2.5 people, they are long-term funded through our industrial income in the group. And as I said before, the industrial income goes directly to our group. But on the other hand, we also have to finance these people by ourselves. So if we do not earn enough, we will not help. We build up debts, and we have to come up with ways to get rid of them. So correspondingly, there's a lot of motivation to do industry work and to do good industry work and also promote this industry work. And this is running very well for long years. And the trend for the future is also positive. However, these 2.5 people that we finance here through industry income, they do not only work on industry. It's not that they spend all their time just on industry. Basically, they are scientists and one technician. For example, Pierre is only 50% funded out of industry in our group. Elsie is working in the energy department where he runs his own group on material development and device development in fuel cell research. David Manes, who coordinates our industry work, he is at the same time our expert for cultural heritage, but also for correlated to wood research, corrosion, and the like. And he also has scientific projects where he has partially project stuff like Sarah, a PhD that finished just this month. And Jan, of course, is our technician. He's not only taking care of our industry projects, but he also supports all of our other activities in the group, from methods to user service to technology development. So he is very active, and I think we are the only group in the lab which has an own technician for the reason mostly of supporting industry requests. And of course, Jan also partially supervises interns and people learning the job. So most of this industry work, and especially that we run our own stuff on industry income, started out with fuel cell applications, which we did until about 2010-12, really a lot, with incomes of beyond $1 million a year. This income we normally shared with the energy department because they provided all the other technical means to run efficient experiments with fuel cells. So all the support that you need. And so over years, that was carrying our activities and was mainly important for our income. And Pierre's role as shared between our group and the energy department came out of this early industry work. And he has done a lot of work also in improving methods for investigating fuel cells, and is still very active. So there's still business going on with fuel cells, but the peak is over. So a lot of it has already reached market readiness. That's how we explain why this business is a bit smaller. But there is, of course, still developments going on, and we also expect further waves to come for the next improved projects. So since this income became smaller, we also had to stretch more for other applications. And some of the first applications we had was in automotive. Diesel particulate filters was an important topic around this time. So our first measurement was on such diesel particulate filters for trucks. And here we could show that we can very well tomograph these devices, but that we can also nicely resolve what happens in this filter, or what is filtered in this filter, that we can distinguish very well between the filter itself, the soot, the ash, but also metallic particles, and that we can characterize full devices in different states. And we published these first works in journals which were important for the automotive industry, especially in Germany. This is also published in German. And this has, of course, a scientific impact of 0. But this was the basis for, again, a good business, because we did this work for nearly the whole German automotive industry. So that was a very important project. But in automotive, there's a lot more that can be done. Another example is looking at a clutch, this time of a motorbike, where the problem of this clutch is that it has problems with the oil inside, with the, how do you say in English? The word doesn't come up. And X-rays fail to see that. And of course, it's very important to see this oil distribution during the operation of such a clutch. And neutrons can deliver that, as you see in the picture down there. Neutrons very nicely can see the pads there, and in addition also the oil distribution around them. And also this was a topic which went this time even into a German-speaking automotive journal, and was a huge advertisement for our capabilities, because this was a visualization of the oil distribution in a running clutch. That means what you also see here, it is important that we are also able to build from scratch and quickly small sample environments that allow us to run devices in the beamline. Is also what it makes very important, that we have, of course, a technician available, but the whole PSI has a very flexible and quick teams of technicians which support this. And in addition, Anaxam, so the new intermediate between industry and our applications, is very much set to take on building such things, to also look at moving things where you need to put in some effort to build it. So then here is an example where I can even show you which company we worked for here. That was about the car damper system for Audi. And this is the example that we have also on our web page. Unfortunately, I didn't get the movie running here, but I invite you to visit our web page and watch this movie. Again, a part where you first create an impact, and then you resolve on the millisecond time scale how the system relaxes and goes back to its original state. And this was an important project for Audi, because it had problems with the dampers and their dynamic behavior. And all these things, they always also have an impact on new customers, on especially from the car industry. They see that they have a method here where they can look through compact metallic devices and still watch the inner workings, and especially oil distributions, liquids distribution, and so on. Then we turn a bit, we go to energy. This is a relatively recent example where we worked for ABB, which is a very strong local but also international company here. What we did here, we were looking into ceramic varistors and in the sintering process. So ABB had the problem that depending on how they sintered and how many pieces they had in the oven, they got different results on how good the binder was burned out of these varistors. And this, of course, impacted the quality. So they wanted to know if we can see the binder content, and we first looked into the numbers, and we found that we can do this. And for this work, we also got some support from a little industry funding to do this first project. And we did these investigations, and we helped ABB to optimize their burning in the oven so that they could get rid of the binder material to a level where it doesn't impact the quality. And this was published in a scientific journal, but it was also found a lot of echo in local media that PSI was able to help ABB, so both local, very important institutions or companies to improve their workings. And there is also still work ongoing and further work after this first application. Another application in energy, here we talk about electric steels, a very important material and a big market. It's used for electric motors and all kinds of electric machineries. And these materials are rolled, and they have a very good magnetic characteristics. But to build them into machines, you have to work them, you have to cut them, you have to stamp them. And this impacts the magnetic properties. And why I like this example, because this uses a relatively new developed method that we developed also in particular here at PSI, creating interferometry, which enabled us to see the magnetic domain walls in such materials, even if they are coated, which they need to be for the machinery. And we can very well characterize the magnetic domain structure. And the problem is when you cut this, this metal, then the domain structure gets disturbed where you cut them. And what we did was basically to qualify different means of working them, of cutting them, from bench pressing, mechanical shear, to lasering. And you can see that there is a big advantage of the lasering. And there was work for companies going into optimizing the lasering in order to not destroy the domain structure at the edges, which lead to significant energy losses. Then medical, this is a relatively recent work from 2 years ago, where we worked with Roche, a pharmaceutical company, and they found they had a problem with the syringes, that they had clogging in there, which blocked them. And of course, then this product doesn't work anymore. That leads to complaints and other difficulties. And they were looking for means to see in their stored syringes the clogging, and according to this, find out how this clogging comes, how it is influenced. And in this case, they had their own project on this already with a scientist. So we could also publish this work, as you will see later. But most importantly, we could show that we can very well not only see the filling state of these needles, but we can also see when they're clogging, when it is crystallizing and cracking. So this allowed us to make studies on the closed syringes in their natural environment and after storage and under different conditions of storage to investigate the effect of clogging in order to avoid it. Another study also took into account the temperature, and you can find the results of this again in scientific journals published. What is important here that again these publications led to a huge request internationally to do such investigations for companies all around the world, and we're currently very busy with such studies. So then I changed to another obvious example, that is aviation. This is an older example. In the Airbus, for example, they use a lot the clear materials, or lightweight but very strong material, a glass laminate reinforced. And here we were studying how different orientations of the fibers impact the load behavior and the failure behavior. And you can see here in these exemplified images, here the cracks under load appearing, and that the cracking under the same load is not appearing when you have diagonal orientation of the fibers to the load direction. So this is a simple insight, but it obviously helped this company. And now one of our biggest, yes, I will try to hurry. One of our biggest applications currently is that we are working for Dassault Aviation for the Ariane 5 and Vega rockets, where we inspect or where we do the images for inspecting pyrotechnical elements like fuse coils and igniters to release the booster rockets. This work, interestingly, you see here some elements, has to be done on film. So we have revived our capability to work on film. We went to a 2-year-long qualification phase and finally achieved that. And now we are in full production phase. You see this start here of Ariane 5 just in August 2020, so a few weeks back, based on inspecting parts from our side. So I know that there is a company working at the Reactor of McMaster University in Canada, which has to inspect all the engine turbines for airplanes in the US market. And this is a similar business, but this is of an order of magnitude that we can still manage, and it brings us a good income and is very important. So how do I continue? Good. For that, we had to do a lot of preparation work. I just want to say in the end that, of course, also with our stress diffraction, we do industrial work. This is mainly stress scanning on components which are prone to failures for different companies. And more money is, of course, on longer term material development. And here we are especially strong in studying complex load conditions, because we have this biaxial loading machine which we can put on our engineering diffractometer. And there we also had important collaborations in the past, and we're working on getting this also going. And with that, I thank you very much, and I'm open for question and hope I was on time still. Thank you.
Okay, thanks very much, Marcus. So a lot of wonderful examples there. We've got one technical and one non-technical question. So I'll start with the more technical one, first of all, from Alan Hewitt, asking about what field of view and resolution is most requested for neutron imaging. Is there a difference between industry and academia in that respect?
Yeah, in general, I can say that the industry tends to the bigger fields of views, because we're looking at components which are often of some 10 centimeters, or when you think of the particle filter, that is, I think, about 35 centimeters. So this is relatively large. But we also see a lot of applications when we think of the syringes, where smaller fields of view of a few square centimeters is enough. And that is also, I think, the most requested when we think of scientific applications.
And then from Mark Johnston, and I have a sort of related question to do with, so I think this relates partly to this company, Anaxam. He's
Yes.
asking whether there's a team at PSI that facilitates contact between the scientific and technical teams and industry clients. So are they between you, or how does that?
So this was what I was trying to outline. Of course, we have this technology transfer team, but that is general for holding general contacts or organizing visits or something. But the actual active contacts where experiments result and business results is normally directly between our team and industry. We go a lot to conferences. You also see our strategy in publishing in the right journals for industry. And so that industry directly comes to us and knocks our door without any mediator in between. So now Anaxam has been founded, and Anaxam is trying to make exactly this mediator. And of course, there's maybe not too much to increase on the business of my group, but other groups maybe have more potential. And I think this is where Anaxam is going. And of course, Anaxam is also taking some work off our shoulders there. As I said before, Anaxam is open to provide sample environment and devices which are specific when you have to run an engine, when you have to run, you always have to build something. And they can do this because they also get some public money support. And so I think there's a good synergy there, but it will not so much change our way of working. If a customer comes directly or through Anaxam, will in the end not be the biggest difference for us.
Okay, a question from Andrea Ponzecchi. Sorry, I've got that pronounced that wrongly. Asking about work on wood. Are you planning to work on wood or wood-related materials?
There's not in the context of industry, but we have a number of projects which, by chance, our coordinator of the industry work, David Manes, he originally comes from wood research, and he's having different projects here with EMPA and ETH in Switzerland, but also with a Canadian university and the university in Sweden. So we run several projects on wood at different states of working. So we do research with Neutron imaging on wood quite some.
I say we have had a very expensive Italian violin at ISIS, so we do wood and cultural heritage at the same time. And again, Klaus Dieter always with another question. You've got both the synchrotrons and the neutrons. Is there any cross work on the imaging and diffraction, or is it really separate?
Is this now again with respect to industry? I would say
imaging and diffraction.
I think with respect to industry, our works are quite separated. But of course, when we have problems that we can't solve, but we know that synchrotron can, or the other way around, then of course we hand over companies to the specialists on the other side. This is normal. And otherwise, in scientific work, of course, there are the named and well-known complementarities, and there is a lot of groups working on both sides, including stuff from my group, which is doing also, of course, X-ray and synchrotron experiments.
Okay. Sorry, we've got another question? No. Okay. Can I ask a final question? This is, I mean, because this is an ILL ESS user meeting, this making the distinction between a national facility like PSI and the international facilities like ESS and ILL. This may be a commercially sensitive question, but basically, I presume you get to decide what you charge, right? Whereas an international facility, it's kind of got to be the same as it costs all other partners.
There is some freedom in what we charge, but of course there's also a rule what the whole thing costs us, and how we do this. Then we have a certain freedom. For example, when customers are also open to publish, then we can give discounts and so on. But basically, there is a fixed price for an application. But if we see that there are difficulties, we can sometimes organize to relieve these issues. There is also the possibility of local funding, which is basically supporting high tech, and they can come in with some 10,000 at least to support the company to have the possibility to have this analysis done, also they could maybe not afford it. So there are different means to overcome such issues.
Okay, so thank you very much again, Marcus. So you round of applause.
Thank you.
And we'll now have a break until 15:15 for the next talk.
work is ongoing on the cave for Bifrost as part of the preparations that are being made for the first set of instruments that will be ready for first science in 2023. Behind the instrument halls are the laboratory buildings that were almost fully equipped when the work had to stop due to the pandemic. After adopting the workplace to the new safety requirements, the installations will be completed with no delays. Last but not least, the ESS campus, with office spaces for all ESS staff, is almost finished. The Move to Campus project has been initiated to secure the possibility to move in as planned in the first quarters of 2021. Even though we're not all in Lund every day, we do progress in building a facility with the aim of getting first science in 2023. We call it business as unusual.
Do you want to optimize your products? Do you need to analyze how your preparations behave? Why not use SANS, Small Angle Neutron Scattering? SANS lets you explore the microstructure of liquids and solids at scales ranging from 1 nanometer to 1/10 of a micron. Why is it useful to know their microstructure? Imagine you want to manufacture a shampoo with a brand new active molecule. The problem with active molecules is that they are often hydrophobic. They dilute very little in water, and shampoo is an aqueous preparation that is used beneath water. Therefore, the active molecules are encapsulated in aggregates of surfactants, but the mixture is very liquid and not very practical to use. So, a thickener is also added to the mixture, but manufacturers don't want an excessively viscous, glue-like mixture that is difficult to get out of the bottle. So, how do you best proportion each ingredient to obtain an attractive shampoo, which is stable in a wide temperature range and over time, and which is easy to rinse off? This is when things start to get really tricky. SANS measurements help you optimize your formulations. They let you observe how the molecules in your shampoo are organized. How does this work? A product sample is placed in a SANS instrument. The instrument is temperature controlled, and an injection system allows blending if necessary. A beam of neutrons is directed at the sample. The matter of the shampoo deflects some neutrons from their trajectory. A large detector records the position of these deflected neutrons. The result is curious figures, which the experts will analyze. This measurement makes it possible to determine the shapes, sizes, and spatial organization of the scatters of structures in your shampoo, ranging from 1 nanometer to 1/10 of a micron. It's even possible to detail the size and nature of the lipid layers or bilayers, the barriers that encapsulate the active molecules. SANS is a major technique that is also applied to many other systems: polymers, colloids, biological macromolecules, emulsions, pores in solids, aggregates in alloys, and even magnetic microstructures. Available in neutron centers, SANS gives you a novel perspective on the organization of microstructures.
ESS is located on the outskirts of Lund, a city with a long, rich history. It's built on the border between the city and the countryside on 75 hectares of land, and it is here the future will be formed. This is where it all starts, the iron source manufactured by INFN in Italy. Plasma is created from hydrogen gas, and the protons are separated from the electrons. These protons are then drawn into the accelerator, where they're accelerated to speeds approaching the speed of light. The 602.5 meter long accelerator is divided into a warm section, a cold section, and a section for which is set aside for future upgrades. What we see here is mostly the cryogenic system that will cool the accelerator. While the accelerator tunnel is mostly 8 meters below ground, the equipment that powers it is placed in the gallery on ground level. They are connected through stubs placed along the tunnel. When the protons hit the tungsten target wheel, the spallation occurs, and the neutrons are released from the tungsten nuclei. A moderator then collects and moderates the neutrons before they're guided towards the instruments. ESS will have 3 instrument halls surrounding the target. The largest is for the long instruments, which are up to 180 meters from the target. ESS will have 15 instruments online by 2026 and has planned for a total of 22 state-of-the-art instruments. This is where the magic takes place. Each instrument is tailor-made by scientists, for scientists, to make the most of the neutrons. As a facility focused on the users, ESS will provide the scientists with beam time at an instrument, as well as a scientist that can help these visiting researchers make the most out of every instrument. The ESS campus, where the scientists will stay during their time at ESS, includes a restaurant, auditorium, conference rooms, and office space for all ESS employees. We will move in at the beginning of 2021. ESS has more than 500 employees representing over 50 nationalities. First science is set to take place in 2023. We will deepen our understanding of the world around us and perform research on scales never seen before. Together, we're on our way to change the world for the better.
The Institut Langevin is the world's leading facility for research using neutrons. The ILL was the first international research center to be based in Grenoble. It was founded out of a desire for European cooperation, shared first of all by France and Germany, and then also by the United Kingdom. The ILL is a research infrastructure dedicated to serving scientists from around the world. It offers them access to the world's brightest neutron beams, a suite of state-of-the-art scientific instruments that are constantly being further developed and upgraded. The expertise of its in-house scientists, engineers, and technicians, who are all specialists in neutron science and technology. Every year, the ILL welcomes some 1,500 visiting scientists and generates around 600 scientific publications. The ILL's neutrons are used to investigate matter in a wide variety of fields: magnetism, biology, particle physics, to name but a few. The fundamental research conducted at the ILL has many applications, for example, in the health and energy sectors. More than a quarter of the research carried out is on industry-related topics. The ILL is governed by the United Kingdom, Germany, and France. 10 other European countries have signed scientific membership agreements with the Institute. These international collaborations make a significant contribution to the scientific excellence of the ILL. Once their experimental proposals have been selected, the scientists from the partner countries have privileged access, free of charge, to the Institute's facilities. Today, around 500 people from 30 different countries work at the ILL. The training of future generations of scientists is one of the Institute's top priorities. At any given time, there are over 40 PhD students working at the ILL, as well as many other student trainees. The ILL provides vital information for the development of innovative solutions to many of the major challenges facing the world today. For the past 5 decades, it has been putting its leading-edge science and technology at the service of society.
Okay, we're ready to restart. No.
I bet you feel like you're on your own.
Yeah. Okay, I have access to the, I cannot access my video, but I could access my mic. They say that I cannot activate the video because it has been.
Wait a bit, let me.
Show your presentation.
Yeah, okay, let's try with the presentation then.
Inverti more.
Then I can start my video.
Okay, we have the video.
Yeah, okay, do we have everything now?
Okay, so the next speaker is Anne Imberti from CNRS in Grenoble. And she's going to talk to us about neutrons for structural glycobiology. Thank you, Anne.
Thank you for the introduction and for this opportunity to talk about structural glycobiology to this multidisciplinary audience. So first, I should maybe define a little bit what is glycobiology. Well, when you see one of these cells in a biology textbook, there is no glycobiology here because they forget about the glycans. So the glycans are the sugars that are at the surface of all our cells and all the cells of living organisms, and they form the glycocalyx. So everything is covered with sugar in the form of glycoprotein or glycolipids, and the glycans are this complex branch structure that are at the surface available to the exterior. So because they are complex in terms of chemistry, you see the monosaccharide, in terms of branching and in terms of dynamic, in fact, they contain a lot of biological information. And this is what we call the glycocode. And this glycocode, the way it is written by enzyme, decipher and erase, this is glycobiology. So we are interested in lectins that are the receptors that can decode this glycocode, that can read it. And lectins are proteins that are, let's say, involved in the cellular communication. They are on some cells, recognizing glycan on other cells. They are circulating in the blood, or they are also on pathogens. And we have a database that we maintain with more than 2,000 crystal structure of lectin, that's unilectin 3D. And you see that they are everywhere, from virus to bacteria, animal, and plants. So there are many lectins ready to read this glycocode and the information. What we focus on are the lectins from a pathogenic microorganism, because this is a way that many pathogens bind to our tissue and recognize them. And for example, influenza virus, it has lectins to bind to some sugar on the surface of cell. And the lectins are different for human flu and for bird flu, because the glycans are different between human and bird. Cholera toxin also attached in the gut by lectins, or staphylococcus, and I will talk more about Pseudomonas. So because pathogens use this sugar to anchor, we can lure them, we can compete with them for attaching. And this is already done in a natural way, for example, in human milk. Human milk contains many free oligosaccharides, and these free oligosaccharides, they compete with the pathogen, with the glycan, with the pathogen, and they block infection. So it's a way to protect baby against infection. And we can do the same in an artificial way by designing glycodrug, oligosaccharides that can interfere with the binding. And in this way, we will block infection without killing the bacteria, so it will not give rise to new resistance. So it's a way to fight multi-drug resistance that can be a very big problem in the future years. So focusing more, I will talk about some organisms that are involved in infection in cystic fibrosis patients. So cystic fibrosis, it's a disease that is due to a mutation, and this creates problems with different organs, and in particular in the lungs, where the mucus is more thick and create inflammation. And the pathogens that create problems and morbidity and mortality with young adults with cystic fibrosis are Pseudomonas aeruginosa and Burkholderia cepacia, that are bacteria, on the fungus, which is Aspergillus. And in the past, we characterized the lectin that are produced by this organism, and they are used by them to attach to the lung of patients. And we solved the X-ray structure of all of them. And we also discovered that they attach to a special sugar, which is fucose. So fucose, it's everywhere, but it's more abundant in people with, or in tissue with inflammation. It's a signature of inflammation, and it's a very good target for this bacteria. So we know about the binding site. We know how fucose, which is a small sugar here, is give strong affinity with leg B because of calcium ion in the binding site, or with BAMB-L and the IFL here because of apolar contact with tryptophan. So what do we want more to design an inhibitor? What we want is to have more details in the binding site. And in particular, we want to know if the acidic amino acid that bind to calcium and sugar, if they are protonated and where are they protonated. We want to have details on hydrogen bonds. What is the directionality of hydrogen bond with a protein? We want to know the exact role of water molecules because they are creating a strong interface in some cases. And for the hydrophobic contact, they are more important than we thought at the beginning. So we want to know the detail of CH of the sugar interacting with aromatic amino acid. So for all this, we want to know the location of hydrogen atoms, and even with the best X-ray structure, we don't have access. So this is why we turn to neutron protein crystallography to see, no, maybe not the hydrogen, but the deuterium atom. So this is the level of details we want to have. And also one of the other advantages is that we will have ambient temperature crystal and not cold temperature. There are some limitations that are due to the low flux of neutron. And this explains also why there are not that many neutron protein structures in the protein data bank at the moment. In fact, there are only two structures at the neutron for lectins. One is from a plant lectin, concanevaline A, and the other one is for a human lectin. But you see that there is no crystal structure of lectin from pathogens, which will open a whole domain. So we need neutron for the structure, but we also need deuterated biomolecules. And this is illustrated on the crystal structure of this human lectin, galectin, complex with lactose. That's a beautiful work that has been done in Lund, where we should be today, so by the group of Derek Logan. So you see that the protein is deuterated, but the lactose here is not deuterated, well, not per-deuterated. It has been exchanged against D2O. So the hydroxyl group are deuterated, but not the aliphatic group where you have CH and CH3. And because of the particular property of hydrogen, and especially of the negative sign of the coherent neutron scattering, this causes problem. And the neutron map, the one that you are really interested in, is not of good quality for the ligand, for the sugar moiety. And in fact, it's a problem where you want to model the ligand in the binding site. You have no information for certain region because of the cancellation created by the hydrogen in some part. So what we want to have is deuterated ligands also to get fine details about the binding site. So deuteration, well, to get per-deuterated protein now, there are excellent possibility with the deuterium lab. And tomorrow there will be also a conference about per-deuteration. So this is something that can be not easily, but can be done. Now for sugar, the story is different because if you look at catalog, the only per-deuterated monosaccharide is glucose. And this is obtained from plant, from algae, and then the polymer of cellulose is degraded and you can obtain per-deuterated glucose. But there are no other monosaccharide available. So we have to do it ourselves. There are two possible strategies. Either synthetic chemistry, which would mean to exchange each isotope on each carbon here, and carbohydrate chemistry is painful, and this will be even more painful. So it's really a difficult work. And the other strategy is to convince bacteria, microorganisms, to do some synthetic glycobiology. So synthetic glycobiology is something we know how to do in my institute at CERMAV, because since 20 years, Dr. Eric Samin has been developing engineered bacteria to make engineered oligosaccharides. So you should know that sugar, they are not made from one gene, like for protein. You have one gene, one protein. For sugar, it's different. If you want to make this trisaccharide, you need a whole cascade of enzymes. And all these enzymes, they have to be introduced in a pathway in an engineered bacteria. So for example, this is one bacteria that he engineered to produce this, what we call fucosyl lactose. And this is one of the oligosaccharides that are now added in infant formula to mimic human milk. So with this oligosaccharide added in milk, you have a better defense for the baby. So it took this bacteria, this strain that he already prepared, and modified it again with 3 different modifications. One fucosidase to cut fucose, so now fucose is produced, and deletion of some genes, so fucose is not reutilized by the bacterium. So with this complex system, we can now start to try to make fucose and deuterated fucose. So this is where starts the work of our student Lukáš. First, he had to adapt the new strain of bacteria, this engineered strain, to work with D2O and glycerol, and diglycerol, deuterated glycerol. Then he had to produce all this E. coli cell paste. Purification is not that simple because you have fucose, which is a small sugar, but it's mixed with other small molecules like lactose or IPTG. So you have to design a precise purification procedure and then characterize the result after purification by mass spectrometry and NMR. And here at the bottom, you have a deuterium spectrum for fucose that can be produced. So at the end, we have the satisfaction to obtain a quite good amount, 220 milligrams of lyophilized per deuterated fucose, which is sufficient for the study. Now we have fucose, we also need lectins. So as I told you, Pseudomonas, one bad opportunistic pathogen, we want to study the B lectin, and the lectin was then produced by classical way in the deuteration lab to get 4 milligrams of per deuterated protein per gram, so quite good amount. And we also studied a different lectin, which is a model because it's not a human pathogen, it's an insect pathogen. It makes this insect fluorescent, and I will tell you why there is some magic in this protein, so we wanted to get it, and we also produced it. So now we are back in a quite classical neutron structural biology project. We pass the bottleneck of production of per deuterated molecules, protein and sugar, purification, that was not that simple. And the classical bottleneck now is crystallization, because we are speaking about neutron and we need big crystals before the hopefully easiest part of neutron diffraction and solving. So this is where the magic of our photorhabdus lectin appear. We knew that this lectin, the hydrogenated form, make big crystals in few days, few weeks. You can get 2 millimeter size crystal with the lectin. So it serves as a model system for us. And we were lucky because the deuterated form with deuterated sugar also gave good, reasonable size crystal. It was not the same story with D. legB, the Pseudomonas lectin, the one that we really want to study. And our student, he had to feed and care for the lectin for weeks and weeks, adding a little bit of protein in the drop every week and really surveying it. But at the end, we had millimeter size crystals also for D. legB with per deuterated fucose, which was quite a challenge. From this, we moved to the LADI3 beamline. This is the Laue diffraction beamline at ILL, and I will not give you details because I'm not a specialist, just to say that this one has been the instrument that gave many of the neutron structure that are in PDB now. So from this, with our model system, our photorhabdous lectin, from 80 hours of exposure, we could get diffraction data, Laway diffraction data of quality. And after 2 weeks of such measurements with 19 images, we could get the structure. So next step is refinement. And I was, as was said by Mark Johnson this moment ago, it's better to have in parallel neutron and X-ray data. So in this case, what we do is that we took the same crystal that was used for neutron diffraction, and at room temperature, in fact, it was at IBS because there was a problem at the moment with the X-ray at ILL, but at IBS, we did exactly on the same crystal, the X-ray measurement. So at the end, you can compare and you can complement the data. So the green here is the electron density map from X-ray, and the blue is the map, the density map from the neutron. And you can really see how the neutron improve the clarity of where the hydrogen, well, the deuterium atoms are. And in this particular case, we can really visualize the apolar interaction between the CH phase, the apolar phase of the fucose, and the aromatic residue, and also the methyl group here of the fucose on another tryptophan residue. And this will be of importance for us, for example, for parametrization of force field for calculation on sugar and protein. So this story now is on the last step of refinement, and in parallel, we continue on the lectin from Pseudomonas. And in fact, the big crystals that took 6 months to grow, they were having too much of mosaicity at the end, and we have to turn out to smaller crystal. But you see that even with this reasonable size crystal, it was quite good. And this is quite useful to have Twitter when you're, because of coronavirus, you're not in the collection room. So from Twitter, Matthew could send us some excellent diagram from this crystal. And this was during the last run of beam time. And now we have preliminary data. Just want to show you how this neutron map is complete. There is no cancellation because of all the deuterium on carbon here are perfectly seen in the neutron map. And we have excellent, let's say, density continuation for the hydrogen bond between the aspartic acid here and here on the fucose. So from this, we will have more details, and I'm looking forward to see also the effect of the calcium ion on the position of deuterium and what will happen. So conclusion from this is that deuteriation of glycoligands really improved the structure in the binding site, and it's a way to go for protein carbohydrate interaction. And we have tools by synthetic glycobiology to obtain not only deuterated fucose, but other deuterated sugar if needed. About perspectives, this was done with LADI, but with a new measuring station DALI, which was presented before, we will be allowed to use even smaller crystal, or let's say more complicated crystal with larger units cell system. So the future should be even better with all these tools. I would open a little bit, let's say, beyond structural glycobiology, or glycoscience in general. So glycoscience is just the science of sugar, and sugar are everywhere. And in Grenoble, we have the GlycoAlps network with more than 100 researchers working on sugar in one way or the other. We are not looking at food, we are looking at complex structure and complex materials. So sugars that are in the cell membrane, glycolipids, in cell wall, like in wood, that are in our tissue, glycolipids, glycan, glycoproteins, that can be made as drug, or that also can be used as smart glycomaterials, hydrogel, and the economy associated. And we do believe that the ILL, as we have, let's say, way to interact with ILL, and in fact, it's already running. We have some people working, as we say, in glycolipids of membrane together with ILL, or some gels also together with ILL, and there are possibility in the future for more interaction between neutrons and glycosciences. So this work has been done between ILL and CERMAV. CERMAV is on the campus, ILL is on the other side of the city, between the group of life science at ILL and structural and molecular biology, glycobiology at CERMAV. And the common denominator is Lukáš, who is here, and he spent most of his time at ILL, but did some of the experiment in CERMAV for preparing sugar. And here are the people involved, and I say Lukáš did the work, and he is on the PhD program of ILL. And I thank you for your attention.
Thank you, Anne, for that excellent talk on the glycobiology, and particularly with the perspective at the end about opportunities. We have one question from Mark Johnson, actually, asking if there is the possibility to use quantum chemistry simulations to confirm the structures you determine.
Excuse me, if you can say what a simulation?
Can you use quantum chemistry simulations to confirm the diffraction structures?
Yeah, in fact, we did that on this fucose binding lectin from Pseudomonas, because it has calcium in the binding site. So we really, we already calculated how the charges are delocalized between the protein and the sugar, and where are the charges. And I'm really looking forward at the detail of the structure to see how it agrees, and if we can maybe refine our quantum calculation to check this, because it's a very special lectin. It has a very strong affinity for monosaccharide, which is quite rare, and we believe that this is due to this charges delocalization. So for this, the neutron structure, which will be quite helpful in combination with the quantum chemistry.
Okay, thank you. A question from Zoe Fisher at ESS. As deuterated sugars are of huge interest for nutrient protein crystallography, do you think it will be possible, even easy, to create other engineered bacterial strains to generate other types of deuterated sugars apart from fructose? And what are the challenges? Yeah,
at the moment, the challenge is that we are building sugar based on the lactose, because our system needs an initial acceptor. We cannot just build sugar on their own. So you have to put something on to build on that. So we have to get a proper construction. At the moment, we're already doing galactose, and this will be quite useful. But I mean, the CERMAV here, we have an excellent team in synthetic glycobiology, and if there are some interesting collaboration, I'm sure it can be open.
I had a question that sort of leads on from that, which is, I mean, you said for one of the examples, I think it took 2 weeks to do the measurement on LADI, but it took you a year to do all the biology and prepare the samples and grow the crystals, or something of that sort. So
well, yeah, I would say it's more the first years of the PhD, which was really devoted to obtaining the deuterated molecules. But since we knew that it was something innovative and we could publish it, it was not too dangerous. But that's really difficult in this kind of program, that for the 3 years of the students, you really wish that you have a structure at the end, because a lot of time is devoted, yes, to the preparation of the biomolecules. Yeah, more than 2 years and 1 year. Yeah.
So the neutrons, or even the time it takes to do the neutrons, are not the limitation.
Yeah, that's reasonable in this case.
But where would you get the tipping point? Because one of the questions is making large amounts of deuterated material, presumably what these growing large crystals. Where is the tipping point which would change that? And you could then produce the samples much more quickly if you only had to do much smaller amounts.
Yeah, well, I think you don't embark in such a program if you are not sure that you will get quality crystal. And in this case, we had this magic protein that crystallized easily. So this was our safety system in case everything else fails. We know that the student will have this protein easy to crystallize. But I agree that I don't know where, there are several bottlenecks, and you have to pass all the bottlenecks. Yeah.
Yeah. Okay. So wait a minute, maybe we have another question just come in. Yeah, another question from Svemir Rudic at ISIS. Did you try to perform spectroscopic measurements on glycoligand crystals?
No, this is a good suggestion, and maybe we should do it. Yeah.
Okay, thank you. Okay, so thank you again very much, Anne. Thank you. Okay. So the final talk of today is by Sylvain Désert. So it's changing subject quite specifically again. So we're now going to the International Society of Neutron Instrument Engineers, which used to be known as DENIM, but now it's known as ISNI. So Sylvain, the floor is yours.
So do you hear me?
Yes.
Do you see my presentation? Okay, so it's perfect. So thank you, Robert, for the introduction. My name is Sylvain Désert. I am engineer at LLB in France. Sorry, I will just change. I'm engineer at LLB in France, and I would like to thank the organization committee who invited me as an official of the International Society for Neutron Instrument Engineers, which is also known as ISNIE, to give a presentation about the developments and challenges in neutron engineering. So the outlook of my talk is straightforward. I will begin with presenting the ISNIE, and then I will review the tools, trends, and challenges facing neutron instrument engineers nowadays. But before beginning, I just would like to make a disclaimer, because along this presentation, I will be using a lot of examples from ESS. And the reason is I wanted to gather as much information as I could from ISNIE members. And many ISNIE members, European, are involved in the ESS project. So don't see anything about this. It is obvious that all the other facilities are using the same kind of tools, trends, and have the same challenges. Okay. So concerning the International Society for Neutron Instrument Engineers, is ISNIE. This society is for technical people and also for scientific personnel. It's not reserved only for engineers, because the idea is to welcome every people involved in the instrumentation or maintenance. Okay, the objectives of the society is to share knowledge, promote best practice. So another way to say is don't do the same mistakes as I did in the past, is to provide networking and expert panels. And it has some tools to do so. So I will give a little more detail just after, but the DENIM conference. So to bounce on your remark, Robert, DENIM is the name of the conference, is not the name of the society. There is also a website, summer school, and newsletter. So the society was created 3 years ago. It has already 231 members from 31 international institutes from 21 countries. So about the tools of the society, which are also tools, of course, for the instrument engineers, is a yearly conference called DENIM, for Design of Neutron Instrument Meeting. So it is a 3 days meeting with plenary talks, then presentation, various presentations like lessons learned, which sometimes people can present where they've been wrong in their design, and it's very interesting. Sometimes you learn more from the mistakes rather than what is going well. Get information about new instruments, some new tools, some preparation of transfers. So it's very versatile. There are poster sessions, and something very interesting are the breakout sessions, which usually last 2 hours, and registered people have to select one of the topics, and it's more or less like a brainstorming session where people can speak about the way and their practices in their own facilities, so they can see how people are doing. It's also a possibility to ask questions, because all the panels of people here are coming from many different facilities, so it's very interesting. We couldn't have the DENIM this year because of COVID. pretty much the same for this conference. Still, the past week, we had a virtual conference for 3 days that was only 2 hours per day. And the reason is we are an international society. So as you can see, the 2 hours meant for the US people, the beginning of the conference at 7 in the morning, and it was ending for Australian people at 11 in the evening. So it was pretty nice for European people. Still, it was good to see that the audience was very high, and in fact much higher than to the other conference we had. And the answer is most probably because people could attend, and these people may be people who are not granted to travel usually. So it's a good point so with this tool. The ISNI organizes a summer school. It is a satellite of the NIM. It is a 1 day where 1 or 2 topics are deeply studied. We have expert lecturers that can give a lot of information, and this is a very nice tool again for either young engineers when they want to know everything about a subject, or even for experienced engineers when they don't know, for instance, maybe vacuum or shielding. They can come for 1 day and then they will get all the information and also all the contacts of the people, so they can keep contact and ask questions in the future. The topic that is foreseen for next year will be sample environments. The ISNI also has a website which is hosting archives from past NIMs and summer school. It also hosts a forum where it's possible to ask questions, technical questions, exchange information, and job posting. So here you have the link. If you would like to come and join, it's free. And if you're interested with neutron instrumentation, you will be very welcome. Also, if you register, you will get newsletter where you can get information. So concerning the advertisement is finished. So now I will review some tools, and I will begin with software tools, 3 of them. The first one is simulation for shielding design. And I took the example of the Dream sample cave at ESS. This is a view from the top of the design. It's a casemat, a concrete casemat, about 10 meters times 10 meters. The neutron beam will come from this area. The sample will be located here. And here you can see the labyrinth footpath for the users. So in the past, calculation were really back of the envelope calculation to design maybe the density of the concrete and the thickness required. Now this has changed with these tools. The designer has to input the information from the source term of the facility is simulating, and the data concerning the concrete choice, density, etc. And then the software gives a dose map of usually is used the worst case scenario, the worst sample you can get. But this allows to check, for instance, that the 1.5 microsievert per hour, which is a maximum dose rate requirement from simulation at ESS, is fulfilled with this design. So you can see here that this simulation helps us to design and another wall to prevent direct view from this open here. Second software tool I wanted to speak about is a tool to simulate instruments. So it's known like Monte Carlo simulation, and it's pretty similar to the molecular dynamics that the scientists are used to use. Name of this one is MaxStars, but there are other versions available. So Monte Carlo software will provide the design a set of components like from reactor spallation source components, neutron moderator, neutron optics, which is what mostly interests the engineer. So the static parts like monochromator, guides, collimator, but also moving elements like velocity selector or choppers. It also provides a sample environment, also models for samples and detectors. So this tool is really useful because it allows to simulate an instrument, possibly with very complex optics, which are really beyond calculation capabilities. So the engineer can pick his instruments, then he can send billions of neutrons on the way that will be simulated. And at the end, he will be able to check what is the flux at the sample. He can check where he's losing useful neutrons, can change parameters. So it's a really interesting tool. And I don't think any new neutrons instruments are being designed now without these such tools. The third software I wanted to present is optimization algorithm. The aim of this software is to converge very fast on an optimized solution. It can be engineering solution, it can be Monte Carlo simulation, like I just presented before. And the idea is to provide some parameters which we would like to optimize. And in case there are many parameters, it can be really time consuming to test all the possibilities. So the aim of this software is to take these parameters, feed them into a software that you will trigger. So this software can be Mathematica, MaxStats, whatever software you need to perform your calculation. And out of it gets a result, which will be your figure of merit. Figure of merit can be, you would like to optimize the flux on the sample. You can want to have a very homogeneous magnetic field, for instance, whatever you want. And from this result of the figure of merit, there is a closed loop, and the software, with the help of some algorithm, will try the best change of your parameters. So this way, the software gives you surface response for each of your components, which are plotted with respect to your figure of merit. So from this, you can directly find your optimized parameter. And this was used for the dimensioning at LAD, for instance, for radio frequency curve code. And to get the optimal parameter took about a few days, whereas doing everything by hand and trying all the configuration would have taken a few months. Another kind of tool used by Neutron engineers now is the additive manufacturing. It is possible to use and print directly from boron carbide, where boron is a neutron absorber. So you can see here, for instance, 3D printed honeycomb. So this is quite simple, but 3D printing allows to print components that are not possible to be machined. So this is really interesting. And on the right picture, you can see that you can assemble many parts to build a large collimator in this case that was tested at SNS. Another tool is improvement of supermirrors. Supermirrors are not new, but they are improving. Now it's possible to get about any geometry, straight line, parabolic, elliptic, whatever shape you want. And you have here on the right side the example of a guide which transforms a square guide onto an octagonal shape, circular-like shape. Now it's also possible to build complex shapes, that you can see here. This would be very important for the renewal of H15 at ILL, which we need to feed 5 instruments. So it's possible to coat on super polished aluminum and copper, which have much higher flux resistance to neutrons. So this will be really useful to get these elements very close to high neutron flux. And also the supplier are able now to coat the mirror up to n equal 8. So n equal 8. So this is a curve you can see here with a reflectivity still of about 40%. It's pretty good, and n equals 8, for those who don't know, means that this multi-layer has a critical angle which is 8 times larger than the critical angle of the natural nickel. So it means it will be possible to reflect either smaller wavelengths or for given wavelengths to reflect larger angles. And this is important when now we would like to work with parabolic and elliptic, for instance, mirror. I also wanted to present a tool, virtual reality. Some people might have at home. It's pretty straightforward to get one. You need to buy an headset, remote controller, sensors. You need to have a space of about free space of about 3 × 3 square meter. Then you buy a computer, an adequate software, and for 10 to 15 €, you can jump into your designs. And this is not for fun. I think it's really a useful tool for the engineer. So here, for instance, you can see we see somebody who is inside the instruments. We can see in red what he's seeing. And it's very nice to be able to evolve inside the future instruments. For instance, the engineer can really look and test operational scenarios, for instance, because it's possible to interact inside the model. For instance, if the scientist wants to change a sample environment, he can really simulate it and see if he has enough space, or if anything bothers, or is he missing some utilities. So it's really nice. Also, it's nice to communicate with people about your project. Now, most of the projects are multi-partner, European. So in the case of DREAM, it's a German and French partnership. So when we are speaking about things, one picture is better than 1,000 words. Now I move to trends, and I begin directly with the trends about instruments. Now many instruments are using a multi-analyzer principle. So I took the example of Bifrost and ESS, which is an inverse geometry spectrometer, where the principle is that the neutrons that will be scattered from a sample located here will transmit through a set of 5 monochromators, and each monochromators has a different angles. So according to the Bragg law, the neutrons with the right wavelengths will be reflected. So I use different colors here to show, and they will be collected at the bottom of the tank with detectors. So what you see here is a cut of the instruments, which represent only one channel, but in the future there will be many channels to be able to measure all the wavelengths and also all the angles in one shot. And you can see here it's 5 monochromators with different angles. Of course, there will be also a complex disposition of the detectors at the bottom of the tank to collect the neutrons. Now I will also speak about new trends, 3-4 slides about detector, and I will begin with detector coverage. On the left side, you can see the lock instruments, which is a sounds instrument. Scattered neutron will come from the left. You can see there are 3 detectors that will work simultaneously to collect at the same time the largest angles here and the smallest angles will go through the whole detectors here, and they will be collecting on the last detector. So the idea is really to be able to measure the full Q range in one shot and get a dynamic in the order of 3 orders of magnitude dynamic in Q range. On the right side, still the same principle, but this is for a high resolution power diffractometer in Japan, where the sample here you can see is completely surrounded by detectors. New detector technologies. So this, when I say new, it's a development from already a few years. And this was following the helium-3 crisis and the increase of the price market for helium-3. So the idea of this detector is to use boron-10. So boron-10 is a neutron absorber. So the idea is to have a coating of aluminum support with this boron. when a neutron interacts, is absorbed by boron, alpha particles are created, and this creates charges inside the surrounding gas. And these charges are collected by a cathode. So this is the collection of the charges is exactly the same as it was with the helium-3 before, just the helium-3 has been replaced by the boron 10. Now, as a scientist, you should know that alpha particles can be stopped very easily. This is why this coating needs to be very thin, in the order of 1 micrometer. This thin coating also means that the probability of absorption of the neutrons with a coating is weak, so there is a low efficiency. This is the reason why this setup has to be reproduced n times in series, so that at the end the efficiency meets the requirements. Okay, so this technology typically is called the multigrid, and this is what will be used for the C-SPEC instrument at ESS. You can see here how it looks like for one module, neutrons coming from the left. And from this module, you can see on the right picture that it's possible to stack a lot of them in the translational axis. And so it's possible to build a fairly large detector, up to a few meters. Other new detector technologies are the scintillator. And I took the example from the SCAD instrument at ESS, where the scintillator is glass enriched with lithium-6. So lithium-6 is a neutron absorber also. And when a neutron interacts with a lithium-6, it creates visible light. This visible light is collected with this component that you can see here, and which is a multi-photo multiplier, which you can buy off the shelf. And it has 8 × 8 pixels of 6 millimeter each. And it's possible, as you can see here, to stack 2 by 2 of these modules to build a tile of 4 components. There is no dead space in between. And also a very nice feature is that, as you can see, the whole electronics, counting electronics, is completely hidden behind those detectors. This means that it's possible from this tile to build whatever size detector you want. And in the case of SCADI, the idea is to have 2 detectors of 1 meter square each. Last detector technologies I wanted to mention is back to helium-3. And this is what is being done at ILL, because I assume they have some stocks. And I also learned that they were able to buy some helium-3 some years ago when the market dropped a bit. So there are many projects. I cannot mention everything, but very large detector banks. Also, very nice feature to see is the direct machining of the channels along the banana shape in aluminum blocks. And also the new development of a multi-beam monitor, very versatile for sharp at ILL. And all these detectors can have been modified also to have high counting capability. A word about reflective optics, which is a real trend these days. And I would like to just explain the principle. And it's possible to make any combination. Here, just for the principle, I will show parabolic with elliptic setup. So parabolic means you have a blue here is a mirror which has a shape following a parabolic shape. So it has its focal point here. And then you have a second mirror here following an elliptic shape. And this mirror has its first focal point, which is exactly at the same location at the focal point of the parabol. And its second focal point is located here on the detector plane. It can be also on the sample. It depends on the application. And according to the geometrical properties of hyperbolas, when neutrons follow the optical axis and is reflected on the parabolic mirror, it will be focused on the focal point, and any neutrons from the focal point and reflecting on the ellipse will be focused on the second focal point. So as you can see, all the useful neutrons exiting here will be focused on the detector. Then a slit diaphragm here is inserted and can be opened or closed, as you can see, because this point here is imaged here. So it's completely possible to change beam subside and minimum scattering angle. In this case, if you put a sample here, you have a small angle instruments with a very high flow capability. Very good advantage of reflective optics, because it's the reason why it's a trend, it's achromatic. So it means it doesn't depend on the wavelengths, which was the case when using lenses. So just to show briefly an instrument where this principle of reflective optics is being used is a reflectometer at ESS, ESTIA, where you can see it uses 3 elliptical mirrors. Each of these mirrors has a length of 7 meters. The first mirror is used to focus the beam onto the what is called the virtual source, where we put the slit system, and this plane is imaged onto the sample in their case. And then there is 2 other elliptical mirrors. One could be enough, but 2 are used because the second one is used to correct for the geometrical aberration from the mirror, and also it enables the team to add some nice features for polarizing. So the advantage of this setup is that there is really low background, because there is no need to add some slits just in front of the sample, and the slits produce background. So the beam is tailored in this position here, so very far from the sample. And as you know, what is important when you're doing experiments is not only the signal, but it's a signal to noise ratio. So if you can decrease your noise by a factor of 10, the signal to noise ratio has a gain of 10. Another trend is the use of adaptive optics. Still in the same manner for the reflective optics, you can see here in blue, this is a mirror which follows more or less a parabolic. You can see an incoming beam which is focused here in this plane. And then by, as you can see here, by changing with an actuator the orientation of the mirror, it describes another parabola, and then the beam, you can see, can be focused to another position. So there is a prototype of this at PSI, 500 millimeter long, with a parabolic shape that you can guess more or less here. There are 12 actuators, and the system is able to focus the beam between 120 and 300 millimeter. So this is really good, because guide optics usually are straight. It's difficult to exchange them. Here you can really model your design and focus and adapt it to your sample environment on sample side. Another trend that is robotics. This has been used for a long time in industry, but here the NMX instrument, which is crystal diffractometer, will be used using 2 kinds of robots. One robot for the sample, to be able to exchange sample and to locate it and rotate it in the beam and perform scans. And then also you can see the 3 detectors which are being held by robots, and they are able to virtually position the detector wherever you want in the space, depending on the scientist requirements. Concerning challenges, first I wanted to speak about remote handling. This is especially true for the new very high brilliance source, as will be the case for ESS. After 100 days of beam, the dose rate activation will be really important. Even after a few days, there will still be the order of 500 microsievert per hour. So in order to perform maintenance, this will be done from the top of the bunker and with remote handling tools. So I decided to present one of these tools which have to be designed in the case of Odin at ESS in order to get out a simple guide element here. The team developed the use of captive fasteners which because obviously when you unscrew a fastener, you don't want it to be able to fall so that you cannot get it out. When the support will be unscrewed and freed, then in order to get out the whole elements, you can see there are some guide rods that will allow to take the components out without interaction with the neighboring components, which are pretty close, as you can see. But also, it is not possible to get this component stuck. So obviously, the rods have to be quite loose. And when you will get the system back into position, then there are kinematic mounts that you can see here that will be used and which will be able to have very reproducible placement.
Can you finish in a couple of minutes?
Couple of minutes?
Yep.
I was told that I could get a bit more because I have the advantage of being the last talker. So I try to do very fast, yes. 2 minutes.
People might leave before you finish, but anyway.
Okay, I try to go fast. Another challenge concerns survey and alignment. This is a general concern. I wanted here just to show what the engineering team of the Estia instrument. So you remember, this is a reflectometer. In order to fulfill their requirements, they need to have an uncertainty of about 10 micrometers on some of their elliptical mirror. So for this, they developed an inspection tool here that you can see on the trolley that is able to measure in real time and make an online survey. It's possible to scan along the length of the full length of the elliptical guide. And in case some alignment needs to be done, then every mirror has few actuators that can correct in real time. Another challenge I wanted to mention concerns IT and data management. At ESS, real-time and data processing and analysis is envisaged. You can see on the right with a nanosphere model when during the measurement and recording there is a feed of the data. Also, you probably heard the talk from Mr. Gutz this morning about the fair data strategy that ESS will follow. This means that for any data, all the meta data we have to follow. And so the raw data, all the motor position, everything, and the analyzed data will represent approximately 2.5 petabytes per year. And also the policy of ESS will be to keep record of this data for 10 years. So it's a huge amount of data. And so the bandwidth network required within a few years to exchange all this data with this value. And another big challenge would be to use artificial intelligence integration. This is a real challenge because, as you could see in this example, the nanosphere model was imposed, but it would be nice in the future to have the software being able to know or find for you what is the best model according to other information. Maybe you can feed it like other measurement being performed elsewhere. So of course, this will require to have trust, scientific accuracy, and reproducibility. So very fast, concerning mechanical choppers at ESS, there will be requirement of choppers turning at 350 Hertz. So it's about 21,000 cycles per minute. You can see it's quite asymmetric. Diameter 70 centimeter. Also the one from Fuya will be very challenging with 1.3 meter diameter, 60 Hertz, and as you can see, fairly asymmetric. So the engineer need to find suitable materials to undergo this stress, also to study the vibration and perform tests to check this is possible. And the last challenge that I call the Holy Grail, I will come on it just now, and I present it. This is the spectrum of the intensity depending on the wavelengths. This is from a cold source at the end of a guide somewhere in the facility. And as you know, the detectors are not able to know the wavelengths of the neutrons. They are just able to say when the neutrons came off. And because of this, to be able to calculate the Q value, it is one has to use these monochromators that will select a thin bandwidth of the spectra, and you can see directly from this that all what is white here is lost for the instrument, for the measurement. So many neutrons are lost. So this holy grail and very challenging would be to invent an energy sensitive detector that could be able to say this neutron has this wavelength. And this way, many instruments, at least all the elastic instruments, would have directly a gain of 100. Everywhere, every facility, you would just need to change the detector. Of course, the gain is huge, 2 decades, and is at the same, yeah, it's really challenging, but the challenge is also very difficult. Okay, so as a summary and perspective, I gave an overview of the tools, strengths, and challenges faced by neutron engineers nowadays. I hope I could convince you that ISNIE is worth and is also a great tool for engineers and also for scientists. There are many other challenges that I wanted to speak about, but no time for it, and you can ask me questions about this point if you want. I wanted to mention the hybrid on sources, being able to build tabletop instruments pretty much in the same way that some lab can have X-ray small instrument in their lab. Component availability also is something is a challenge for the project of instruments when many kilometers of guides are being, for instance, ordered by many facilities and the suppliers are limited. And also, I mentioned a bit for IT, artificial intelligence, but I'm sure AI can be implemented for design of the instruments. So I would like to thank all the ISNIE members who helped me to build this presentation. I also thank, of course, non-ISNIE members, maybe future, and you for your attention.
Okay, thank you very much, Sylvain, for a very comprehensive overview of neutron instrumentation and the challenges ahead. There's a multi-part question from Andreas Freund, and I think if I just allow him to talk, it might be easier. So, Andreas,
Okay, do you hear me?
Yep.
Yes.
Yep.
Okay. I would ask you if you have connections with industry, because to my experience, it is very useful and beneficial to involve them into this kind of industrial developments so that they're able to respond to the demands that are coming out of
I would say
the neutron community. And the second topics, sorry?
No, please go on.
And the second question would be to get mutual information between the synchrotron radiation community and the neutron scattering community, because the problems that you mentioned on active adaptive optics, monochromators, and reflective optics, they are common to both fields of research, and maybe you could inspire each other by having some maybe common meetings.
Okay, so thank you for your questions. For the first question concerning link with industry, I would say that the ISNIE is open to companies, so they don't have exactly the same rights for the forums, because we don't want them to be able to influence, but still a lot of companies have members, and they can attend the meetings. It's possible to speak with them, and so these companies keep track of the needs. When I was speaking about super mirror and guide companies, these guys know very well the situation. Also, it's true we have to produce a lot of code for tenders for our instruments. So companies, we had through the brightness contract, we organized a few meetings where we invited industrial people to warn them. I think it was at least 3 years in advance of our project and the call for tenders we will have to do. So I think they are quite they were quite informed. About the second question, I totally agree with you, and I can also give an example of very nice. It was not a common meeting, but it was a denim conference at PSI in 2018, where we invited people from the X-ray that could give some presentation also, because we wanted also to get links with them. And I can give an example when one of my colleagues visited I'm sorry, I forgot, visited the ring at PSI. He saw one instrument that was using an element that could I'm sorry. So I do it. I will explain it another way. I was looking for an instrument for a telescopic nose to support vacuum. We want to limit the air. So this telescopic part needs to be always as close as possible from the sample. And the point is, for the SCADI instruments, we have very low space to crop for the user to crop under this nose extension. If he needs to go the other way. So I wanted to build some kind of telescopic nose that can rotate this way, but we didn't. This was not invented anywhere in the Neutron community. We were thinking how to do it, and when we visited at PSI, so 2 years ago, so I'm back on it now. My colleague saw from this synchrotron exactly what we wanted to build under vacuum. He got all the information. He saw he could, and so we went back and decided to copy the system. So I completely agree with you that I'm sure we have same kind of problems, sometimes not in the same scales, because usually neutrons, we can say it's more agricole-like, but yeah, totally agree with you.
And it's worth noting that, for example, the sample environment collaboration spread from neutrons to now neutrons and synchrotrons as well. So that.
Yes, it's true. Yeah, many ways of doing links. For instance, next year, if we can travel again, it is planned to have the next denim at in Japan, and this is exactly where will be the next sample environment conference. So we already try to have one common day for the conference. And that's why you could see today, I plan to have the summer school with sample environment.
Okay, and then the final question before we finish. So from Adrian Rennie, he's saying, is there a significant overlap between the Neutron user community and instrument engineers? Because most users interact with scientists at facilities. And if not, do you think there's a benefit to bringing the instrument engineering closer to the users?
Thank you, Adrian. I don't think from the, when I look at the members from the ISNI, that there are so many scientists. And the scientists I know, they really have a second hat about engineering. So I consider them like engineers, more than scientists. So it might be, well, it's not the purpose of the society to have scientific, only scientific people, because it's really linked towards techniques. But what I could say is that all the engineers we have and all the projects that we are working now we are always buying with a scientific leader and engineering leader. So I think it's already the case. We have good ideas of what the scientist is looking for. Well, it depends on the facilities, but from my part, I have good ideas what the scientist is looking for, what are the key parameters important for him. So it's good because it's possible to advise him and sometimes discuss. So it's good, or maybe it's bad sometimes when the engineer can say to the scientist, maybe he's asking too much, but it can ease the communication.
Okay, so thank you very much, Sylvain. Thank you to all the speakers today. It's been a very, very interesting day, and we start tomorrow morning again at 9:30, finding out who the Neutron users are and what they do. from Lambert Van Eyck. So thank you to everybody. I'm afraid you all got to go home now, so or be at home.
Thank you. Have a good evening. See you tomorrow.
Okay. Bye.
Bye-bye.